Good afternoon, everyone, and welcome to the final presentation of the Eco Lunch and Learns sponsored by the Bermuda College and BEST for this season. We're pleased to welcome Chartered Meteorologist Dr. Mark Guishard, who is Director of the Bermuda Weather Service, a section of the Bermuda Airport Authority. He holds a PhD in meteorology from Penn State University, a master's in atmospheric sciences from the University of East Anglia, and has trained at the UK Met Office and the US National Hurricane Center. Dr. Guishard has over 20 years of experience in weather forecasting, disaster management, research meteorology, and catastrophe risk science. He is a fellow of the Royal Meteorological Society and is also a trustee and adjunct faculty member of BIOS, with research interests in climate change, natural hazards, and disaster resilience. He has served on numerous local, regional, and intergovernmental committees focused on disaster risk, reduction, early warnings, and mitigation of natural hazard impacts. We're delighted and very privileged to welcome Dr. Guishard to us today. Thank you.
Thanks very much. Can I just confirm that you can hear me okay? Okay, could I just have a confirmation from you that I can be I'm being heard okay before I start?
Sorry, Mark, we'll use the comment to communicate with you, but we can hear you just fine. Thank you so much.
Great,
thank you. There's a few other people on, so you can see a comment section or the chat. So people are there. People are there and ready. Thank you so much.
Thank you very much, and thank you to Bermuda College and BEST for hosting this talk. Very interested and very timely, of course, to get into some detail here. So without further ado, I'll just I'll crack on. Thank you very much. So today I'm going to be talking about the past, present, and future of Bermuda's hurricanes, all the way back from perhaps 1,000 years ago to the present and what we might expect this season, and then into the far future as what we might expect under a warming climate. So first of all, I'll start off by introducing Bermuda Weather Service, which is where I'm presenting from today. I'll talk a bit about some hurricane basics to refresh the audience's understanding of what a hurricane is and some of the things we should be aware about. Excuse me. And then I'll run into this this timeline of hurricanes, dropping out from time to time to focus on elements of our risk and resilience, and sort of wrap up by thinking about what we can expect in the near and the long-term future. So to start off with this introduction for the Bermuda Weather Service, we're a section of the Bermuda Airport Authority. We have 13 staff, 10 of whom are Bermudian. And as with many small islands, the requirements for us to have our own meteorological services on the island, that stems from the legislated and regulated need to provide weather information in support of aviation safety and air navigation. But the resources needed for an aviation service do happen to enable the development of a 24/7 service provision for the public and marine stakeholders as well, and for also providing warnings and advisory services for a wide range of natural hazards and climate change. So we've kind of evolved over the last 25 years from being the effectively the airport weather office to the National Meteorological and Hydrological Center for the island, also offering climate services. So we have responsibilities under that arrangement for working with not only local agencies, but international agencies as well. We're regulated under the International Civil Aviation Organization for Bermuda's safe air navigation and aviation meteorology. We have representation on the World Meteorological Organization under the UK as a member state. And in particular, the heavy focus is on the Hurricane Committee, the Regional Hurricane Committee, which just met last week. So we've got a seat at the table, as it were, regarding matters surrounding hurricane activity in the region. And also BWS serves as the Bermuda's tsunami warning focal point under UNESCO Intergovernmental Oceanographic Commission. So we wear a number of different hats, not only locally, but regionally and internationally, and liaise with multiple agencies beyond Bermuda. So after that brief introduction, I want to let's talk about hurricanes. As you heard, my background's very much in meteorology, and my PhD's very much on hurricane science. And we spend a lot of time in during the hurricane season, which spans from June through November, discussing the current state of storm activity in the Atlantic directly with the U.S. National Hurricane Center. But what are some of these basics that we need to sort of refresh our memory on every once in a while? Well, first of all, there are several different things that control hurricane activity: their formation, their intensity, their characteristics, where they go, et cetera. One of the biggest controls on hurricane activity is warm ocean water. So the warmth, the heat of the ocean provides the energy, the fuel, if you will, for hurricane activity to really get going. And so the warmer the water is, the greater the propensity for hurricanes and tropical storms to form and also to intensify. So there's a very well-documented direct relationship between the heat energy in the ocean, the upper ocean, and the propensity for hurricane activity. One of the other things that controls hurricane activity, however, is wind shear. And this is when if a storm, a tropical storm or a hurricane moves into an environment where there's a lot of different strength winds with height. So the surrounding environment is such that you have lots of very fast winds aloft. It means it can disrupt the in, up, and out circulation that goes hand in hand with a hurricane, and can shear it apart. So this vertical wind shear can actually stifle the development of a hurricane and even prevent them from forming. So these are two things I want us to keep in mind during the course of this talk: that warm water is very important for the development of hurricanes, and sort of vertical wind shear can inhibit the formation of tropical cyclone. That's a tropical storm or hurricane. And there's many other factors that are necessary but not in of themselves sufficient for the formation and intensification of hurricanes, like you have to have a moist environment. You have to have the storm forming far enough away from the equator that the spin of the earth can give it some rotation. You have to have an atmosphere which is conducive to vertical motion as well. But the two things I want us to keep in mind are warm ocean water and vertical wind shear. When we think about hurricanes, one of the first things we consider is their intensity, and that intensity is measured by this wind scale, which is known as the Saffir-Simpson hurricane wind scale. And it categorizes the wind speeds of hurricanes, such as Hurricane Katrina, you can see here in the Gulf of Mexico in 2005. It categorizes those, the hurricane intensity by its maximum sustained wind. So what a hurricane basically is a large, low pressure system, low pressure at the surface, with very fast winds spiraling in towards the center of the storm. In towards that center of low pressure, which is often characterized by a well-defined eye in the most intense storms. So this Saffir-Simpson wind scale focuses on the maximum wind anywhere in this circulation, and looking at the same different representation of the same storm at the same time, based on its wind field. Basically, the wind scale, the Saffir-Simpson scale, characterizes the hurricane by how intense the maximum surface winds are at one spot, or like what's the most intense wind in this entire circulation. So it's safe to say that the Saffir-Simpson scale does not represent all of the characteristics of a storm, only that maximum wind. And so when we think about very large storms that might be weak. They might have a very large wind field that can cause damaging conditions for days and days. Or if we think about a very tightly constrained, intense system, you might have a very high category, but a very small chance that that intense wind is going to impact anywhere. So I guess my point is that the Saffir-Simpson scale that we tend to always reference, category 1, 2, 3, 4, or 5, does not necessarily represent all of the hazards, all of the risk associated with tropical cyclones. And again, that term I use, tropical cyclones, is what a meteorologist such as myself would tend to call a tropical storm or hurricane. It's more of a meteorological term. Now, the most intense systems we tend to call major storms, major hurricanes, and those are characterized by wind speeds of 96 knots or just over 100 miles an hour and up. So the maximum sustained wind within the circulation is of that threshold or greater. And once we get to category 5, there's no upper limit. There have been calls in the recent past by scientists and others that that we might want to introduce another step in the wind scale, category 6. That is very much under lots of debate at the moment. So for now, at least, and for the foreseeable future, we have this wind scale that we categorize hurricanes by. One aspect that is definitely not treated that is very important to hurricane activity and their impacts in our region that is not characterized by this wind scale is storm surge and storm tide. So very quickly running through this element of hurricane activity, you can see this on the schematic here that storm tide is made up by a number of different elements. First of all, the tidal phase is very important, just the average, like what is going on in terms of it being low tide, high tide, or mid tide. That's above and below this mean sea level. In addition to that, the storm itself, the strong wind speeds pile up a surge of water ahead of the storm. And also the low pressure can augment that a little bit by sort of sucking up the surface of the sea as well. That effect is not as important as the wind-driven surge. So there's this sort of dome of water that is being developed in advance of a storm and surrounding the storm by that sort of sustained wind that's going on for a long period of time. And we see that often when there's a storm that's moving near Bermuda but isn't making an impact as yet. When we look at, say, Kinley Field Road down by the airport near us here at the Weather Service, where the surface of the water tends to encroach a little bit into the grass. And that's before we get into those windy conditions where you have very active waves as well. So you add the waves on top of it, and the full effect is called storm tide. So high tide, mean sea level, the tide phase, the surge on top of that, and then the waves all build up to this thing we know of as storm tide. And that can be quite extreme in some hurricane scenarios where you have, especially in scenarios where you have a very long coastline that gently, that has a very shallow continental shelf. Luckily for us, we don't have that here in Bermuda. We're sort of like a pedestal in the deep ocean. And so any storm surge that we get does not accumulate at the coastline, but for the most part goes around us. So we don't get the 10 and 20 foot storm surges that you might see in the Caribbean or the Gulf of Mexico. Our storm surge is more like a foot to 3 feet, something like that. So let's think about a timeline of Bermuda hurricanes. And to take a look at this, we're going to go back to before the beginning of hurricane records, before we had people living in Bermuda, before there were ships around to run into these storms and report on them. So how was it we go about figuring out what storm activity was like before we were around to be settlers here in Bermuda? In order to do this, we use a tool known as Paleo tempestology. It's a very long word. Basically, it means the study of ancient storms. I'm going to show you this very short clip here as I'm talking to give you some sense of how this is the baseline for this. So on a coastline here in green, you might have a coastal marsh or peat bog or a small coastal lake or pond. As sea level continues to rise, the area just behind this sort of coastal dune, where there's a peat bog or a coastal marsh, will just gradually fill up with silt or mud or algae or whichever it is that it's characterized by. As there's a storm, as indicated by this hurricane flag, you might get some storm surge and some storm tide, some wave action that blows some marine sediment or sand over the top of that barrier dune and into the peat bog or the coastal marsh or the coastal lake, whatever it is we're looking at here. Fast forward to the current era, and you'll see in the schematic sort of buildings here, and what one can do if one is so inclined as a coastal geologist, is take sediment cores down through the stratigraphy of this feature here. And those sediment cores will reveal each layer that has been blown over. So these, what we know of as overwash deposits into the coastal lake or the pond. Here's an example of one from the US East Coast. And each of these layers corresponds to an historical event, a historical overwash event, usually associated with a hurricane. Now, of course, in some parts of the world, you might expect that these overwash deposits stem from extratropical storms or other types of events, other flooding events. So these are not necessarily comparing hurricanes directly. You can't directly assign each event specifically necessarily to a hurricane, but certainly to a coastal flooding event. So looking at, so that example was not from Bermuda, but this one is. So about a decade ago, there was an effort to sample take some sediment samples from some near shore coastal ponds and lakes, Spittle Pond, and this is Mangrove Lake here. Mangrove Lake is near Tuckerstown, near the golf course. And in each of these locations here, a sediment core was taken. And just in terms of understanding the sort of background, here's the beach, the ocean just to the southeast. And this road here going along the south shore is on top of roughly a 25, 26 foot or 8 meter berm that isolates this lake from, or this pond, I should say, from the ocean. So this Mangrove Lake is filling up with algae over time, and it's because it's isolated from the ocean, it doesn't suffer the effects of mixing from wave action as much as the deep ocean would. And if you don't believe that beach sand and marine sediment can be overwashed over 25 feet or 8 meters to get into Mangrove Lake, here's Hurricane Nicole in 2016. It went right over the island. And this is a picture I took the day after Hurricane Nicole. This is Mangrove Lake behind this wall, and here is some beach sand on the road from the storm itself. So indeed, we can see that there is sediment being blown and washed over that 8 meter berm. It doesn't mean the sea level itself was that high, but it does mean that there was wave action and spray that's blowing that sediment over into the lake. So here at the top are the top left are some photographs of people taking sediment cores, depending on what kind of region you're looking at. The sort of top right photograph is of someone in a boat taking sediment cores in a shallow freshwater environment, and that's exactly what was done in Mangrove Lake. And the results were to find some of the expected results were to find changes in the chemistry going further down. And the sort of two photographs here, the green and the sort of black and white next to it, are actual photographs of sediment cores taken out of Mangrove Lake. you can see that there's some contrast between the darker green, or the darker black in this case, the darker gray rather, and the white layers. Those white layers are overwash deposits from storms. And in those deposits, you see differences in chemical composition, increases in the chemical amount of calcium, which is typical for beach sand, which is made out of calcium carbonate, and also strontium and some other chemicals as well. In addition, one can look at the coarseness of the grain sizes. You can imagine a pond filled with algae is very, very fine and silty, whereas you add beach sand to it, you can imagine that that beach sand is much coarser. And so you can go back in time, effectively, as you're going down into the depths of the sediment core, and create a timeline of actual events. So that's what this graph shows. It shows the sort of top right, highlighted in red, is the individual events that we know about in the historical record of hurricanes that match nicely the peaks in the coarse fraction of grain sizes that those overwash sand deposits in Mangrove Lake. And so by doing that, we can kind of calibrate this whole time series all the way back to something like 1,700 years. Now, you may be alarmed by seeing these huge peaks down here at around 150 centimeters. And I think one of the things we should take note of is that the coastline didn't always look like how it looks like now. And so these massive peaks don't necessarily correspond to incredibly strong hurricanes, but they certainly correspond to overwash deposits. And to kind of demonstrate that, we can look backwards in time from the bottom right, which is an aerial photograph of the area. You see the road and the development near the road and between the road and the beach around the Pink Beach development. And if you go back in time, 1941, you see there's a lot more just basic beach and sand encroaching on that road area. Go further back in time, you can see that again for the 1941 aerial photography. You go further back, sort of 200 years or so, and you can see that the original surveys of the island had indicated that there may very well have been an inlet into that area, so some 200 years ago or more. So, you know, this is all pointing to this idea that, okay, we've got this very interesting data set, but we should perhaps take it with, if you'll forgive the pun, a grain of sand or a grain of salt. Nonetheless, it poses some interesting comparisons with other places in the region. So if you look at Puerto Rico, for example, where a similar study was done, you see these intense peaks of hurricane activity. You look at the Bahamas, some periods of ups and downs in hurricane activity. Massachusetts, likewise, ups and downs in hurricane activity, or at least overwash deposit activity. And then looking at Bermuda, it seems like there's been a somewhat consistent high level of storm activity throughout the period. So the kind of conclusions of this Paleo study were that over 1,000 year period, there were several intense events, but in comparison to all these other places around the region, Bermuda always seems stormy compared to places like the Caribbean or the East Coast of the United States. So that's an interesting conclusion to that overall study, is that we have this notion that Bermuda is always stormy, regardless of the phase that other jurisdictions are facing. So from the prehistoric past to the more recent documented historical past, we can look at the numbers of storms that have actually moved through the Bermuda area. And that's what you're looking at in the track map here. These are tracks of all major hurricanes within 100 nautical miles of Bermuda, or what we call the threat range here at the Bermuda Weather Service. And if you sort of compare that with the overall storm activity in the Atlantic, it seems that Bermuda is a good proxy location for tracking storm activity throughout the entire North Atlantic, at least through the historical record going back to the 1800s. So when there are typically peaks in the North Atlantic, in red here, in the red line graph, there are also associated peaks in Bermuda, which is the gray bar chart underlying it. And likewise, when there are troughs in overall Atlantic activity, there are troughs in Bermuda. Just eyeballing it, there's no straight correlation that we've done here, but it seems to be a good proxy. So what does that mean for Bermuda? It means that we've seen a lot of storm activity over our 400 years of being a territory, being colonized, being settled. But there is perhaps a silver lining to that. It means that after the first 50 or 100 years, we quickly realized perhaps we should build out of stone instead of wood. That meant that built into our collective sort of psyche, that in our sort of national psyche, that we've got a sense of awareness and preparedness associated with lots and lots of history of activity. And that's especially true after the last 20 years or so of heightened activity that we've seen here in Bermuda. There certainly have been periods where we've been more complacent, perhaps. That comes coincident with lulls in hurricane activity, but we're now very practiced enough, let's say, to know what to do when a hurricane approaches. One of the aspects of us being resilient is that we're small and we're isolated, and that might be a little bit counterintuitive, but it basically is saying that the sort of relationship between smallness and resilience shouldn't be underestimated. Physically, we have nowhere to go. We've got nowhere to evacuate to if there's a big event going on. And so that sort of breeds self-sufficiency. If we, physically, we can easily get to places that need sort of assessment for damage. It means that if supplies are on hand, they're close to hand if they're on island. But perhaps more importantly, in my opinion, this smallness means that we're connected. We can act quickly, we're agile. The left-hand photograph here on the screen is the stockpiling of resources and equipment and goods and supplies to aid our neighbors to the south in the Bahamas, a good only 48 hours after Hurricane Dorian made an impact. So the fact that we can move this quickly to mobilize resources in a short period of time speaks to our smallness and our connectedness. We're able to help our neighbors when they need it. And closer to home, internally, we can check on our actual next door neighbors that need it when they need assistance as well. So that sort of builds into our resilience. The connectivity aspect is very important as well. We've got very strong internal relationships. And very few places in the world can you get the entire emergency response apparatus into one room. In very few places in the world do you bump into the head of national security walking down the street or the governor in the grocery store. We've got this sort of connection to our neighbors, our colleagues, that cuts through layers of bureaucracy when there's a big event going on. We've also got very strong international and external partnerships that we leverage to our benefit when it comes to challenges that we as a country face. So, in terms of using a professional example, the relationships that we have at the Bermuda Weather Service with the U.S. National Hurricane Center, the UK Met Office, the Caribbean Meteorological Organization, and others enable us to access expertise and information that originates even beyond our shores. And then that goes in both directions. We're able to feed our data into the wider world when there's an event going on. In the bottom right, you see some of us at the Weather Service during Hurricane Paulette, directly liaising with the Hurricane Center, feeding our data, our radar information, our satellite information directly to them, so that they can update their modeling and their forecasts. in real time. So we've got these aspects of connection that help our resilience. So now back to our narrative about the history, the recent history now of hurricane activity in Bermuda. We've talked about the sort of prehistoric storms and how Bermuda has always been stormy, according to prehistoric Paleo data from Mangrove Lake. We talked about the historical record of storms going back 150 to 200 years. In the more recent past, looking at the last, say, 40 or 50 years or so, we have seen some great increases in the technology that allows us to observe storms and track their characteristics. In particular, we have ships that go out and measure the ocean temperature on a routine basis. We have radar data. We've got satellite remote sensing that we're able to detect storms from space. We've got aircraft reconnaissance, weather balloons, real-time data capture from on-site instrumentation as well. So the recent part of the record has really improved in terms of its accuracy of the characteristics of hurricane activity. And so we can leverage that to look at more recent trends in hurricane activity in the Atlantic. So what you're looking at here is a map that came from an academic study on looking at the number of tropical storms and hurricanes that form around the world over a period from 1980 to 2018. So just under 40-year record where there's a detection of trends. And what we're seeing is that in the Atlantic, we're seeing an upward trend in the number of storms that form during that period. And the warmer colors on the chart here and in the color bar here indicate greater numbers of storms forming. The white dots indicate statistical significance. So this is a robust trend that we have seen over the last 40 years or so, that there are more storms forming in the Atlantic. What's that mean for Bermuda? Well, we've looked at this even closer to home, specifically in projects we've done at BIOS, and determined that there is not only an increasing number of storms moving through the Bermuda area, the storms that are moving through the area are getting stronger and stronger. So there's a gradual upward trend in the number and the intensity of hurricanes and tropical storms that are moving through the Bermuda area, and the average sustained wind speed has actually doubled since we started looking at this back in the 1950s. So that's somewhat alarming. Why might this be? Well, go back to what I was saying before about ocean temperature being a strong control on the number and the intensity and the formation potential for hurricane activity. If you look at this chart, apologize for the busyness of it, but it tracks upper ocean temperatures at different layers in the ocean in the peak of hurricane season, August, September, and October. So the top blue here is the sea surface temperature, and going further down into the ocean, down to, say, 50 meters here in green, and further down. And you can see at all levels of the ocean since the 1980s, we have been seeing this gradual upward trend. There are some bumps and wiggles, some ups and downs in the trend, but the trend is most certainly upwards for warming oceans. And that warming ocean is providing more fuel for hurricane activity to continue and intensify. And indeed, just in the last decade, we have seen many storms come through the area. And this is a subset of the ones that have been the most impactful or most memorable, let's say. In 2010, we had Hurricane Igor. 2014, we had a bit of a double whammy with Faye, followed a week later by Gonzalo. 2015 saw Joaquin. 2016, we saw Nicole, which is pictured in the left-hand satellite and radar image there. Umberto came in 2019, and then just in 2020, we had Hurricane Paulette. It's worth noting that last year, 2021's hurricane season, we were fortunate not to have had a direct impact by a hurricane, but Hurricane Sam that sat about 200 nautical miles, 200 miles, I should say, came within 200 miles of the coastline of Bermuda, is the strongest storm ever to come that close to the island. And so that kind of hints at or supports the idea that we are seeing not only more storm activity, we're also seeing more intense storms nearby. And I should mention also that we're seeing a disproportionate number of storms go directly over the island. We had 4 in the last 7 years that have had direct eye passages, including Paulette and Nicole that you're seeing here on the screen in front of you. So here's another representation of that ocean warming near Bermuda. This is sort of measured against a baseline in the 80s and 90s, where it was it's now getting warmer and warmer since the 80s, continuing to increase through just last year. And that's leading to more and more hurricanes being major storms near the island. So there's that link again between ocean warmth and hurricane activity. In addition, if that weren't enough, we're also seeing through detected trends and projected trends into the future, changes in wind shear. And remember, think back to one of those earlier slides where I talked about wind shear being one of those aspects of the atmosphere that can control hurricane activity or constrain it. So we have evidence now that there is reducing wind shear in and around the United States, especially off the East Coast, extending outwards into the Atlantic Ocean near us. And we're somewhere in this region here where my mouse is. So both warming oceans and decreasing wind shear over time. And this region, the East Coast of the United States, is represented by this blue line. Decreasing projections of decreasing wind shear should continue through the century, and we should start to see that being detected separate from the noise, if you will, right about now. This last couple of years, we should be getting into a detectable trend of wind shear that's got this sort of climate change signal, if you will. So all of this, as I mentioned, has led to this increase in major storms. In the bottom, in the right-hand panel, you'll see a satellite image of Hurricane Sam. At its most intense, it was a 130-knot hurricane. Remember, back to our Saffir-Simpson wind scale, Category 5 is 137. So this came in at just about 7 knots under a Category 5, very intense Category 4 storm, and it just sort of moved past us. We were very, very lucky to have missed this one. And here we have tracks of all those major storms moving through the Bermuda area, coming to within threat range over the historical record. So we're seeing much more of this major storm activity in the Bermuda region. And I think it's worth noting that as much as we feel we are resilient, we must not be complacent against increasing storm activity going into the season and the future. Again, looking before we get to the future, let's continue to just finish up on the recent past. This is tide gauge. This is a tide gauge that is on the oil docks just on the north side of St. George's. And this blue line represents the upward trend in sea level that tide gauge has measured. There's a picture of the gauge itself on the oil docks. And so these annual measurements have been going on since 1932. So we've got a reasonable record of this increase in sea level through the years. This is the mean sea level. So this is the annual average sea level. Again, bumps and wiggles around the mean, but you get the idea that it is absolutely, definitely increasing over time. It has been increasing on the order of 2 to 3 millimeters per year, which doesn't seem like much on the face of it, but it does have a definite impact when it comes to looking at storm surge. Not only do we see increases in storm activity, that is leading to increases in storm surge. And we talked about what storm surge is before. It's that wind-driven component of the ocean where the ocean's sea level actually rises ahead of and in conjunction with the storm. So each of these black peaks here are tide gauge measurements associated with an oceanographic event. Most of them are storm surge from a tropical storm or hurricane, but we do have some oceanographic events that are not associated with weather, warm eddies. And we also have winter storms as well. The red lines are basically showing the extreme events, those that are beyond 2 and 3, respectively, standard deviations from the mean of those tide gauge measurements. And you can see, if you sort of squint your eyes, you'll see that there's a gradual increasing of extreme events beyond this this highest threshold. And indeed, Umberto and Paulette in 2019 and 2020 also sort of exceeded that threshold as well. So we are seeing perhaps more intense storms, but we're also seeing more intense storm surges that result from them as well. And part of that is down to sea level rise. This is the highest surge in the record, Hurricane Nicole, that we looked at earlier. But it's comforting to note that Hurricane Nicole and Hurricane Gonzalo, for that matter, their highest storm surges came at low tide. So it's comforting for those particular storms, but a little bit nerve-wracking when we consider if this level of surge had come at high tide, we would have had a much worse impact than we actually did. So let's look at today, the near future. And what many of you will be here to listen to, I've made you wait for, is the seasonal projection, the seasonal prediction for this hurricane season coming up. What we're seeing here is not focused on any one seasonal prediction, but a whole suite of them. This website's been very useful in recent years to look at it. It collates all of the seasonal projections and predictions that come out for the hurricane season. And what you can see in a nutshell is that they're all predicting above average activity, regardless of whether they are private entities, government agencies, or universities, academic agencies. They're all going for a higher than average season. So that's no real surprise when we consider some of the things we've talked about already. The world is getting a little bit stormier in our neck of the woods. And so having a projection of, or a prediction of higher than average, higher than historical average hurricane activity in the North Atlantic is not really surprising. But the mantra we always say during the onset of hurricane season, where we're just on the threshold of it now, is that it doesn't matter what these seasonal predictions say. All it takes is one storm to make it an active season for us. So we should be thinking about preparation regardless of what the seasonal prediction is. And there have been many instances where there's been a lower than average activity in the Atlantic, but we get hit. So I think going back to that Paleo study indicating that Bermuda is always stormy, I think that's a good sort of high level message to take home, that regardless of the seasonal prediction for the whole Atlantic, Bermuda is always at risk, and we need to be prepared regardless of that seasonal prediction. So what about the far term future? Well, I guess you're getting the sort of the message here, the theme that yes, Bermuda is always stormy. Bermuda looks like it's going to get stormier. This is a modeling study that shows the simulated number of tropical storms, or at least the conditions that are conducive to them, increasing near Bermuda under climate change scenarios. This particular scenario was doubling CO2 in the atmosphere and sea surface temperature increasing by 2 degrees Celsius, which is not sort of unreasonable to expect. And the result of that set of simulations was to find that there was increasing formation of hurricanes and tropical storms in the central North Atlantic that recurve, and also increased formation just south of Bermuda. So we should, if all else being equal and this study is indicative of what will actually happen, then we might expect to see as many as one more major storm per decade coming through our region as well. Of course, this is an academic modeling study, so and it's one study out of many. So, but I did want to show this as a potential scenario to be aware of in the future. Now, back to our tide gauge measurements that we saw earlier, where there's a gradual but certainly detectable trend of sea level rise And let's project that out into the future, again, using the best climate science available for that particular tide gauge. And you can see that the projection, regardless of the scenario, the emissions scenario of greenhouse gases, the projection is for that sea level to accelerate, that sea level rise to accelerate, rather. So the sort of message here is that what we consider an extreme event today is likely to be within the norm of the high tide range. Perhaps in as close as just 20 years, perhaps later. It is coming one way or another. It's just a matter of time. And I think being prepared for, mindful of the potential for that to happen in as soon as 2 decades would be a sensible course of action. And all of this, of course, underlies that storm surge risk, which is being enhanced by the very number of storms that are coming through and their growing intensity under a warming ocean. So to wrap up our conversation today, we talked about these long prehistoric records implying that Bermuda has always been a stormy place relative to its neighbors. There's been this very long history of hurricanes that we've faced. Indeed, the very settlement of Bermuda came as a result of a fleet being scattered by a hurricane. So we've got this very long relationship with hurricanes in the Atlantic, in Bermuda, and that has helped to shape our culture of resilience that we have and our responsiveness. But there has been some periods of complacency, and we should be aware of those and not rest on our laurels too much. The recent upswing in activity heralded by, let's say, Hurricane Fabian in 2003 has been likely due to this rapid increase in ocean warming in the Northwest Atlantic and our regional reductions in wind shear. And that storm surge risk is going to continue to rise with sea level. And those long-term projections are for increased storm activity and increasing exacerbation of sea level, of storm surge by that sea level rise as well. So all in all, the message is that the future of hurricanes in activity will continue to be exacerbated by climate change. And a final slide that I tend to now put up at the end of all my presentations is to just remind everyone that we all have a part to play when we consider the response to climate change, whether that be mitigating our own personal or organizational emissions, or adapting to the impacts of climate change as they come forward. With that, I'll say thank you very much once again to everyone, and happy to take any questions at this stage.
And thank you so much, Mark, for that informative and frightening, I might say, presentation. You covered everything I was going to ask, really. But for the audience, if you could put your questions in the YouTube or Facebook chats, we'll certainly put those up for Dr. Mark Guishard to answer. But just to kind of start off the conversation and get us rolling, you mentioned mitigation and adaptations, but in terms of the mitigation, if you could maybe highlight the top 3 things that you would recommend an individual takes on, and then maybe from the community level, what would be the 3 priorities we should consider as a community? So individual and community priorities.
Sure. So individual, you're putting me on the spot now.
Sorry.
Okay, that's why I'm here. Individual emissions, or we consider that our carbon dioxide emissions in Bermuda per capita are very high. They're something near 10 tons of carbon dioxide per person per year. That stems, and we think about the sources of those. That stems from burning fossil fuels to create energy. And those, of course, those fossil fuels are imported by ship. So those ships themselves have energy, so there's a 2-pronged thing there. And then also our reliance on combustion engines for vehicles. So I would say, generally speaking, energy usage could be reduced. And also exploring more forms of renewable energy is an important step to take that we're sort of all taking as a community. If you have the means and the ability to tap into renewable energy resources, one should, but all of us should be thinking about our energy footprint as we think about our carbon footprint. In addition, shipping, I guess, is a key piece. And these are kind of both community and individual. As we bring everything to the island, almost everything to the island, in a very densely populated place, but we have to consider that the more we consume locally, the more that adds to that fuel cost going into shipping. So I think sort of the notion of consuming less, utilizing local resources when possible, as opposed to bringing things in. All of that has an impact on the carbon footprint. And then finally, do we need to drive our bike or our car everywhere? Can we cycle? Can we walk? Can we use an electric vehicle? Can we take public transportation? These are things that are, I guess, sensible, responsible things to do, cost-effective things to do. Will they impact the climate change hazards that are upon us and coming down the pipeline? No, but they will help build our own resilience to adapt to them and be more self-sufficient.
Speaking of self-sufficiency, you showed that image of Bermudians rallying with all of the goods to help out our neighbors. But obviously, with current situations, supplies are going to be under stress. So what do you envision the future looks like in terms of us being able to be that agile and be prepared in terms of being able to rally for ourselves and to help out neighbors?
So I think again, I'll reiterate, we have a lot of historical foundations of our cultural resilience that I've talked about already. We have probably a better handle on how to respond to a hurricane than many places. Part of that is some of the historical reasons I've talked about. Part of that is simply geography. We have this. We don't have a continental shelf that exacerbates storm surge, for example. So I think there's this element of we've got a lot of sort of ingrained resilience, but it would be very easy to be complacent. So to your question about what the future looks like in terms of rallying, I think it would be very easy to sort of rest on our laurels in terms of disaster resilience. I think we're going to see increasing pressure with regards to climate change having an impact on supply chain, especially, not just from what we know on a day-to-day basis, but especially during times of high impact. I mean, not just climate change, but we're still coming through a pandemic. We have conflict now in Europe that's affecting supply chain issues. There are labor shortages in shipping. There are all sorts of things that will affect our supply chain. And I think the supply chain of goods and potentially services coming to Bermuda is a real sort of limiting factor, if you will, to our ability to respond. So I think as much as we're able to foster self-sufficiency internally, that's only going to be a good thing for disaster resilience as well.
Okay, thank you. We have our first question from the audience. This presentation was truly interesting. Do you think we will be getting, intensely strong storms like Hurricane Paleo this season? What are the results showing right now is the main question.
So thank you for that. It's worth pointing out that we're pretty good at the Bermuda Weather Service. We forecast out to sort of 5 days. Usually we've got something like an 85% objective verification. Some of you may laugh at that, but when it comes to projecting through the hurricane season, all bets are off. We don't have a seasonal projection that will tell us where storms will go. What we do know is that hurricanes have historically gotten worse around Bermuda, and so the message there is like, we can't predict when and if there will be a hurricane that impacts us directly, but we can always be prepared for when one is nearby. So sorry, that may not be a very satisfying answer, but that's the best we can do, unfortunately.
No, sorry. Oh yeah, sorry. I have a couple more coming your way. So from Craig Simmons, I'm going to expose him. He's our local economist that is a senior lecturer here at Bermuda College. I'm presuming it's him. Hi, Craig. Have you identified the most vulnerable areas of coastline that need fortification?
So I and others at BIOS, and I should have said that earlier, I have an adjunct affiliation at BIOS. We have been updating a climate change report for Bermuda. That will come as part 2 of the report that'll come out later on this year. So far, Bermuda is a small enough place that when we talk about hurricane activity and also sea level rise, it's almost like everywhere is equally at threat. Now, there are some places that are more vulnerable by virtue of the infrastructure or the buildings that are there. There are places like St. George's that we know is particularly vulnerable because it's low-lying, and it also has a lot of exposed buildings there in that small area in our World Heritage site. So that's an area worth focusing on. But there are others as well. There are sort of low-lying areas where you might have a rest home, for example, or a bridge which might need some fortification. That is yet to be determined, and I know that's very much the public infrastructure side of things is very much the focus of Department of Planning's upcoming report and study, in fact, on sea level rise and coastal impacts and storm activity as well. So again, don't have a great full answer for you there, but I think things are in the work to answer that question by this time next year. So please ask me that question again this time next year.
We had some questions sent to us in advance. This one coming from Celia Curtis. How will the Gulf Stream be affected by melting ice sheets, and how will this affect Bermuda?
Good question. I mean, I think there are these big disaster scenarios that you see in movies where the Gulf Stream shuts down, but I don't think that's on the cards certainly in the near term. And by the near term, I mean in the coming decades. Long term, I don't really have an idea about that. I do know that there are some impacts to the overall overturning circulation that helps to drive the Gulf Stream. I think we're always going to have a transport of heat of warm water out of the tropics by the Gulf Stream, but there has been evidence that it has been slowing down gradually. Impacts to Bermuda, it's difficult to say. There are so many complexities. You have the Gulf Stream. That's one sort of constraint on our climate, and another one that we have is the sort of upper atmospheric circulation cells, which they themselves are changing over time under climate change. So again, I don't have a very clear answer. It's an active area of very complex research, and the jury's still out, really. And in fact, I will say that in our project that we've got to write a report on climate change, this is one of the challenges, is coming to a point where we can say something definitive. Mm-hmm. That is, I mean, there are some things that are very definitive, some things I've talked about today. There are other things for which there's still a high degree of uncertainty because it's still under research. It's sort of unclear how it will evolve. The timeframes and the intensity of some of these changes that are coming are still open-ended questions in the scientific community.
In this report or in your investigation of things all around climate change, is one of the things that you're looking at as a potential, I guess, for the future in terms of being prepared and whatnot, is evacuation and what we can do as an island too. And can that event of the worst case scenario of sea levels rising and storm surges increasing? I mean, because islands are already doing that now, where they have to, have a plan in place for their population who are sinking. Is Bermuda potentially way down the line a candidate for that?
I don't think so. We have our topography is low-lying, but it's not as low-lying as some places, say the Maldives, for example. There are lots of jurisdictions that are extremely low-lying. All those low-lying atolls that you see in the Pacific and the Indian Ocean are particularly at threat from climate change because their highest elevations are something like a meter or two above sea level, whereas ours, I mean, we have a very hilly topography. I think Town Hill is something like 290 feet. So I don't think we have the same kinds of threats from sea level rise as those low-lying islands do. Those are very much existential threats. Whether or not those land masses will exist in X number of years remains to be seen. With Bermuda, I think our challenges are more short-term extreme impacts from, again, I'll come back to hurricanes, because of their frequency and intensity and the battering wave action that goes along with it. So I don't think we're anytime soon thinking about sea levels rising so much that we would be submerged. That's not on the cards as far as I can see. It is worth noting that the report that we're doing is very much focused on what hazards we can quantify and the science behind them, and then also what areas are vulnerable. And that will, once that report is rolled out, then the intent is that is available information for people to make individual decisions, policy decisions, et cetera. But we're not going as far as saying, okay, this is what needs to happen. So to your question about evacuation plans and things like that, I think this any kinds of planning will hopefully factor that new information in, but it's very much in the remit of those that make such decisions.
There was one question that I forgot to ask from Celia Curtis that may be a bit more on the technical side. Is it still true there's a mass of warm air sitting atop the North Polar region, which is destabilizing the polar vortex, causing it to wobble and fracture? If so, how will this affect Bermuda's weather? Good
question. So there is the Arctic and the Antarctic are the places that are warming the most. They're seeing the most warming, which is alarming because they also contain the most land-based ice. So the warming of the polar and Arctic regions means that there's disproportionately more impacts coming from ice melt from there. But yes, to the point about how that destabilizes the polar vortex, from time to time, there is this, you hear, I mean, we've heard it in the press in recent years, this term polar vortex. It's not really a new term. It's something that something that's been latched onto by the media as a sensationalist thing. Basically, what it means is that the circumpolar current, or the vortex at the poles, is occasionally destabilized. So cold air sags south as warm air is sort of injected into the polar regions. And what can happen then is, as that cold air sags south, it sort of drags the jet stream with it. And with the jet stream follow the storm tracks. So the more the jet stream is sort of, I wouldn't use the term destabilized, I'd sort of say wavy. The more that it's wavy, the more it can have big impacts on sort of storms following the same track time after time, having areas that are under what are called atmospheric rivers of moisture. So areas that have lots and lots of either storm activity that move through, or lots of rainfall that gets dumped over a long period of time, or that are just upstream from those or downstream from those that are suffering in terms of heat and drought because they're not getting that water, or they're under a very warm environment. So you can get both heat waves and extreme rainfall events at around the same time in different parts of the world due to this see, you've got me saying it, waviness of the jet stream that happens from time to time. And that does seem to be on the rise because of climate change.
Thank you so much. Some really good answers and questions from the audience, and a lot to ponder. And I see that we are close to time, so I just want to thank you again for sharing your expertise and all that you do for us in Bermuda to keep us safe from storms. And one of those things is preparation and being aware. So if you could leave us with, I guess, one last piece of advice to prepare us for this upcoming hurricane season, and also to prepare us for this impending threat of climate change. I shouldn't say impending; it's here, right?
Yes.
So
Yes.
if you could leave us with,
Yes.
one piece of advice for the audience, what would that be?
I would say now is the time to dust off the hurricane plan if you have one, and really take a hard look at it. If you don't have a hurricane plan, make one for yourself, your family, your organization, your pets, your loved ones, your neighbors, etc. Just have something, and it doesn't have to be anything complex, just something as simple as, if there were to be a hurricane tomorrow, what would I do? Where would I go? Who would I need to look after? What supplies do I need? So straightforward things that we've done in the past, but we have to remind ourselves to do periodically. In terms of climate change, I think the number one thing that people can do is what we're doing right now, is having a conversation, talking about what the potential impacts might be, trying to get to grips with the fact that, yes, there is uncertainty associated with climate change, sea level rise, increasing storm activity, etc. Try to pose some scenarios, learn about it for yourself, and keep listening, keep watching this space. There's always more information coming out, and don't fall. I guess the biggest one is don't fall into despair, because it's not something we can't do anything about. There is action we can take, but if we sit there and stick our head in the sand, then things will be worse for us in the future.
Absolutely,
Thank you.
100% agree. Thank you so much,
Thank
and
you.
thanks to the audience for tuning in. And
Yes.
they can watch it again on YouTube in the future.
Yes,
So
yes.
thank you so much.
Thank you.
Thank you all.
Bye.
Bye.